Hi everyone, today's topic is cosmic evolution. We discussed last class how astronomers believe the universe started 13.8 billion years ago with a giant bang. At that time, the universe looked nothing like it does today. It was very, very hot and dense. So hot and dense that atoms could not exist. We had a sea of elementary particles in a primordial soup. How did we get to the universe that we see today, with its galaxies and stars and planets and people, from that smooth, hot plasma? That's the question we'll try to answer in today's video. I want to start by discussing a famous paradox. It was first enunciated by Olber, and he said, if the universe is infinite, then why is the sky dark at night? The idea behind this paradox is that if the universe is infinite in extent, then any line of sight from the Earth should eventually intersect the surface of a star. So that in any direction you look, you'll be looking at a star, and that would make the whole sky be bright. Of course, further stars will be fainter, but there will be a lot more of them, and so in the end, if you make a careful calculation, you come out with the fact that the sky should just be uniformly bright as the surface of the sun. This is a demonstration that shows you what this might look like. If we look out into a patch of sky and we only have a few stars, then there's a lot of dark sky in between them. But now, once the number of stars increases and goes up further and further, then the amount of dark sky will become lower and lower until once you have an infinite number of stars, then the sky is just covered in brightness. So again, if the universe is infinite, then every line of sight will eventually intersect a star, and the night sky in every direction should glow with starlight. This is obviously not what we see. In fact, forget about stars. If we look out beyond our galaxy into intergalactic space, we see all of these galaxies, but there's a lot of dark space in between the galaxies. So why is it that not every line of sight outside of our galaxy ends on another galaxy if the universe is infinite? Think about it for a little bit, and press the pause button if you need to in order to think, because the solution is coming up soon. So the solution to Olber's paradox, as we have found out in class, is that the universe might be infinite in space. In fact, we don't know if the universe is infinite in space. We think that it's very, very, very large, but whether it's actually infinite or not is under debate, and we might talk about that a little bit more next week. But we know that the universe is finite in time. The universe had a beginning about 13.8 billion years ago. That beginning was the Big Bang, that theory that we discussed in last class. Because light has a finite speed, and therefore takes time to travel from one point to another, there are many stars and galaxies out there that are just so far away that light has not had enough time to reach us in those 13.8 billion years. And what this does is set a cosmic horizon, a boundary to the observable universe, beyond which we can't see. So in this diagram here, we're at the center of this observable universe, and in every direction, there is a boundary. Beyond that boundary are other stars and galaxies, but those stars and galaxies are so far away that light just has not had enough time to reach us yet. So whether the universe is infinite or not in space, in some way becomes irrelevant, because there is a very defined physical boundary beyond which we can never be in contact at the moment. Of course, as the universe ages, the edge of the observable universe becomes wider and becomes further and further away, because time has had more and more time to travel towards us. There's actually an earlier practical limit to how far we can go. We can't actually look all the way out to the Big Bang, to 13.8 billion years ago, and that's because, as Kate discussed in the last lecture, there's a point beyond which the universe becomes opaque, and that point is the point of recombination. So at that moment in time, the universe became neutral all of the free nuclei that were going around captured the free electrons, and so instead of having ionized atoms and free electrons floating around, now you have neutral atoms. And because of this, the photons are now able to travel freely. They're not scattering with the free electrons and protons anymore. And so, because the photons are now free to travel, the universe all of a sudden becomes transparent. When the universe is opaque, it's very hard for us to see back through that time. And so the cosmic microwave background, which is the light that's emitted at that moment in time when the universe goes from being opaque to being transparent, is also called the surface of last scattering. And beyond that, it'll be very hard for us to actually see anything because the universe is essentially opaque. So how do we go further? How do we probe the early universe? How do we know that there was a Big Bang? How do we put together a theory of that Big Bang and how the universe evolved in time if we can't observe the universe before it was 300,000 years old, which is the time at which this recombination occurred? And in fact, how do we even know that it's 300,000 years old at that time? Like, how do we know how much time has elapsed from the beginning of time to this point of last scattering? So this is obviously a very complicated question, but to give you an idea of how cosmology works and how we start answering some of these questions, we basically assume that the expansion of the universe has been happening uniformly, so that we know how the temperature and density are changing with time. And we assume this because we see the temperature change since the surface of last scattering to now, and we can just basically extrapolate from that to the beginning of time and assume that the temperature just keeps going up in this nice, linear way here. So that as you go back in time, so as the number of seconds since the Big Bang becomes smaller, the temperature goes up and it becomes much, much hotter, so that the early universe was hotter and denser, and it's cooling as it's expanding. Now, if you notice the units on this y-axis, these are very, very high temperatures. Temperatures of 10 to the 24 Kelvin are common in the very early universe. And at those temperatures, and therefore at those very high energies and speeds, particles behave very differently than they do at the temperatures that we see on Earth, or even in all of the universe today. And so we see that the timeline of the universe, this is sort of another way to see it. We have the time on the x-axis, and you have, again, the temperature on the y-axis, or equivalently the energy of the particles on the y-axis. And you see that the realm of observational cosmology, what we can actually observe with our telescopes and what we can see in the universe, is really limited to the sort of right edge of this diagram. So that's, we can observe stars and galaxies, and we can observe the cosmic microwave background, but at that point we can make any more observations. And so the realm between that time and the beginning of time is really a realm for particle or nuclear astrophysics. So we need to understand particle physics, and we need to understand particle physics at these energy levels that are, very, very rare and uncommon in the universe today. But we do manage on Earth to recreate some of these conditions in particle accelerators. So this is a picture of the accelerator, the LHC accelerator in Switzerland. If you squint, you'll see that on top of that yellow lift is a man in a blue jacket, and everything else around him is the particle accelerator. And this is an amazing piece of machinery. And in these accelerators, we're able to essentially recreate the conditions very, very close to the Big Bang, about a billionth of a second after the initial explosion, the initial beginning of time. And this accelerator does that by accelerating particles to 0.9999991 times the speed of light. So very, very, very close to the speed of light. And therefore is able to recreate conditions when particles were moving around so fast because their temperatures were so high because the universe was only a billionth of a second old. This is a aerial view of the LHC, just to give you a perspective on how big this thing is. The LHC is 27 kilometers in diameter, in circumference, I'm sorry, and so it goes through all of these. It goes through France and Switzerland in this border here near Geneva. And so underground, under the ground here, is these giant tunnels where particles essentially go around these giant tunnels, and as you can imagine, at these speeds of light, they go around this path in much less than a second. So they're just speeding around in these tracks, and what people do is then they collide particles with one another and they observe what happens. They have these detectors that are able to detect the products of these collisions of particles, which is what we expect is happening all the time in the very early universe. And in fact, recently, the ATLAS experiment, which is one of the experiments at the LHC, was able to finally detect the signature of the Higgs boson, a very important particle that scientists had been searching for a long time, had predicted must have occurred based on what we know about the conditions of the Big Bang and how it evolved. So that was a very exciting measurement that came out very recently. So we can use what we know about fundamental particle physics, and we know these things from doing actual experiments in these accelerators, and we learn about how quarks and protons and neutrons interact with each other when they're moving at these high speeds. And we learn how these things are formed from this initial primordial soup. So at some point, the energies and temperatures are so high that essentially all matter is converted into energy. There is no matter. And as the universe starts cooling down, first these very elementary particles, the quarks, form. And then as the temperature keeps going down and down, bigger matter can sort of assemble into bigger units. And so first you put quarks together in order to make protons and neutrons and electrons, and then finally you can combine those protons and neutrons with the electrons to form neutral atoms from that primordial plasma soup. So when the neutral atoms form is when what we say recombination occurs, because the electrons recombine with the protons and neutrons in the nucleus to form those neutral atoms, and that's the moment where the CMB is created. So there's all this era before we get to recombination that is essentially the realm of particle astrophysics and that we know about from these experiments. This theory, on the other hand, has has been able to make predictions about what the universe looks like today, or what it looked like, close to recombination. And so we can actually go out and test these theories that, that apply to these conditions that are almost unimaginable, but we can test these theories by making observations of the universe that we can see. So for example, one very important prediction to come out of the Big Bang theory is how atoms and nuclei are made in the early universe. So before the electrons recombined with the nuclei, there was an era called the era of nucleosynthesis that happened around 2 minutes after the Big Bang, where the universe had the right conditions somewhat similar to the conditions at the centers of stars today, for hydrogen to combine with other elements in order to form slightly heavier elements. So at that point, we made hydrogen and helium and just a few other, very few other light elements like lithium and beryllium were formed, about 2 minutes into the Big Bang. And the theory of the Big Bang predicts what the fractions were of each of these elements. So here's a plot that comes from calculating these things based on what the temperature and density were doing as a function of time in the universe. And so on the y-axis here, you have the fraction of total mass that's locked into these types of elements, and this is relative to the amount of hydrogen. And on the x-axis, you have temperature on the lower axis and time on the upper axis, and that's just the reason why we can plot both of those quantities on the same on the same axis, is that time and temperature are just directly related. As time goes by in the universe cools down. And so let's say that 100 seconds after the Big Bang, so 10 to the squared, so 100 seconds, the temperature was a little bit higher than 1 billion degrees Kelvin, and at that temperature nucleosynthesis started to occur, and so these fractions started changing dramatically, so that helium was created, and some deuterium, that's hydrogen with the number 2 on top, and some other forms of helium. There's some beryllium and some lithium also produced. And so as the universe keeps expanding, as time keeps going by, so by the time that you get to 10,000 seconds after the Big Bang, or a temperature of about 10 to the 8 Kelvin, or 100 million degrees Kelvin, by then pretty much all nucleosynthesis has stopped, and so the fractions, the relative fractions of each one of these elements is sort of frozen in the universe at that point. So these are what we call the primordial fractions of these light elements, and any changes to these primordial fractions must have happened later in the universe, and as we know, the only places in the universe after this point that are actually capable of performing nucleosynthesis, of making heavier atoms out of lighter ones, are the centers of stars. So we'll have to wait from this moment, after the universe is cooled enough to stop making these nuclei anymore. We're going to have to wait a while until stars actually form in the universe. So these sort of very high overdensities in the universe form that have the conditions at their cores to, essentially bring the temperatures and densities back up to this type of condition and make heavier elements. So this is a very strong prediction from this model, and what we can do is we can go out and measure the relative fractions of these different types of elements in the universe, and actually verify that whether this model is correct or not. And so far, the model has been very successful in predicting just how much of each of these things should occur. And I guess I should say that another very powerful aspect of this model is that depending on a very few fundamental parameters of the universe, like for example how much mass the universe contains, the relative fractions of the light elements that you expect from this primordial era of nucleosynthesis change. So this is what this graph is telling you here. You have on the x-axis, you have how much matter there is in the universe, how much ordinary matter there is in the universe, so one of these fundamental parameters that we're trying to determine. And on the y-axis, you have the abundance of each element relative to hydrogen, and you can see that as you change the amount of ordinary matter in the universe in the model, then the prediction for the relative fraction of each element is also changing, so that by going out and measuring these relative fractions, we can actually gain an understanding of how much ordinary matter there is in the universe. So again, these are very powerful predictions that allow us to really get at some very fundamental parameters for the universe as a whole. So that was before the cosmic microwave background was emitted, so before that recombination era. But what happens now if we move forward in time? Instead of going back towards the beginning of time, let's move forward in time from the epoch of recombination, when the universe looked something like this. It was a smooth, homogeneous, isotropic soup of particles with a temperature at the time of 3,000 degrees Kelvin. Of course, we now observe it to be 2.725 Kelvin, but that's because that light has been redshifted with expansion. But at the time, the temperature of the universe was about 3,000 degrees Kelvin, and it was remarkably the same in every direction you look. Like, the amount of variation about that temperature was really, really, really small. So essentially the universe was just extremely smooth. The comparison that Kate used last time was that at this time the universe was essentially smoother than the surface of a billiard ball, which is extremely smooth. There's just no there's no structure in it at all. There's no lumpiness. Like, everything is just smooth. So how do we go from that, from a completely smooth, completely, where everything is exactly the same temperature and exactly the same matter density at exactly the same constitution, it's the same elements everywhere. How do we go from that universe to the universe that we see today? The universe that we see today, when we look out in space, is extremely clumpy. It's extremely inhomogeneous. It's extremely anisotropic, so not homogeneous at all. There's these places where the density of the universe is much, much higher than it is in other places. It's anisotropic. That means that it's not isotropic, and what that means is that when we look in different directions, we see completely different things. So in one direction, you might look at a galaxy, and in another direction, you're looking at empty space. So how do we go from something that is so smooth to something that is so clumpy? Before we answer that, I want you guys to get a better idea of just how clumpy we're talking about. So how clumpy is the universe today? Well, the average density of the universe, so if you took all of the matter in the universe and you distributed it completely smoothly, so you just spread it out over the entire space that the universe has, you come out with an average density that is 10 to the minus 26 kilograms per cubic meter. To give you an idea, that's the same thing as 5 hydrogen atoms in 1 cubic meter, which is the same thing as taking 1 grain of sand and distributing the material in that grain of sand over the volume of the entire Earth. So that's very, 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 very underdense, right? There's very little density in the universe at large. But if we look at the density of things that surround us, in fact, if we look at the density of human beings, our density is about 1,000 kilograms per cubic meter, which is to say that if you were able to get a cubic meter of human flesh, which is kind of a gross thing to think about, but anyway, a cubic meter of human flesh will weigh a ton. And that seems about right. So anyway, that means that if we're at the density of 1,000 kilograms per cubic meter, that means that we are 10 to the 29 times denser than the universal average, right? Because that's 1,000 is 10 to the 3, and we're comparing that to 10 to the minus 26. So we are 10 to the 29 times, or 10, 1 with 29 zeros in front of it, times denser. Us humans, we are that many times denser than the universe is as a whole. So that's a huge difference in density. So again, the universe is extremely clumpy. And fortunately, we're not actually trying to make all of this structure and all of this clumpiness from something that looks like this. Because as Kate showed you, if you just change the contrast in this image so that you're looking at variations in temperature of the order of 10 to the minus 5, so 0.000001, 0.000001 of the temperature of the mean temperature of this sort of sea of particles, then you find these tiny, tiny fluctuations. And this is what the satellite WMAP was able to see when it had finer resolution. We could see that the fluctuations on top of this sort of average temperature of 2.275 actually exist and are there, but they're less than 1 part in 10,000. Those small fluctuations, at that time, 300,000 years after the Big Bang, are enough to create all of the wonderful structure that we see today. Because all you need is a very small amount of fluctuations, and then gravity takes care of the rest. But let's talk about how we can measure the scale of these fluctuations very precisely from a map like this, and end up making something called a power spectrum. So the measurement that we're trying to make is to see how patchy this picture is, so how patchy the universe is on different angular scales or spatial scales, if you will. So we take this picture and we say, okay, how patchy is this picture on the scale of 1 degree or 10 degrees or 0.1 degrees? And we measure essentially at each one of those sizes, so at 1 degree, and if you look at this picture here, you'll see that the most of those patches are sort of 1 degree in size. Then we can measure how many patches there are at that size, and we can plot this graph that essentially plots amplitude, so how many patches there are versus the size of the patches. And this is essentially a power spectrum. And so this is the data, this is what we measured from COBE, and the model for the Big Bang model that tells you how these anisotropies are created and how they essentially, how their size changes with time, predicted that this is what that power spectrum would look like. So it's an amazing agreement with the observations. But as you can see, COBE was able to constrain the peak at around 1 degree very easily, because the resolution was good enough to capture the patchiness at that level. But as you go to smaller scales, so as you go to 0.1 degrees, for example, COBE simply did not have the resolution to really capture how these fluctuations were happening at those much smaller scales. Before we move on, I want to show you this animation that explains what a power spectrum is in more detail, and I think it's very powerful. This was made by the European Space Agency for their new satellite measuring the cosmic microwave background, Planck. So this is what the power spectrum looks like. Again, there's a very large peak around 1 degree, and then there's going to be smaller peaks at smaller angular scales. But what this is showing you, the red highlighted region is the part of the angular size that we're looking at, and then it shows you what those peaks look like. So again, we're moving to smaller angular sizes, and so the peaks that we're concerned with get smaller and smaller. And as that angular size increases, as the angular size decreases, those peaks get tinier and tinier. So we're essentially looking for how many peaks there are at each one of these individual angular scales. So again, as you can see, as we get smaller and smaller, those peaks become tinier and tinier. And that should tell you that in order to get to the right side of this diagram here, where the angular size is so small, so the patchiness is so fine, you really need a telescope with very, very good resolution in order to be able to capture all those fluctuations that are happening on such tiny scales. So that's why, since the 90s, we've been flying better and better satellites with better and better resolution in order to be able to capture the power spectrum at these very small scales. We need better resolution to go to smaller scales. And again, this is what we were able to do with COBE, and as you can imagine, with the new satellite Planck, the errors on the curve for smaller angles are going to get much better. And so we're actually going to be able to really test whether this model that we have for these peaks is a good model or not. And I think this is one of the most amazing achievements in recent years for astrophysics, which is that we go out and we measure this power spectrum with better resolution so that we make a better measurement, and look what we come out with now. These red dots are actual measurements from Planck, and so that prediction of what those peaks should look like is just amazing, has been amazingly successful. And now, by making these measurements to such great accuracy, we can really start distinguishing from between values for fundamental cosmological parameters, because the prediction of where these peaks are, so both the location of the peaks and the amplitude, so how high the peaks are and how wide they are, all of these different parameters depend on fundamental characteristics of the universe. For example, how much matter there is in the universe, what the geometry of the universe is it flat or curved, what different types of matter there are in the universe. All these things go into the model that then is able to produce this curve. And so now, because our measurements are so exquisite, we can really distinguish between different amounts of matter in the universe. Another way of saying this is that this measurement is able to really constrain the amount of matter in the universe in a very direct way. So we've come a long way since Penzias and Wilson were struggling with bird poop on their antenna, and I really think that this is an amazing achievement of science. So back to that plot, though. This is again those fluctuations in the emission from the universe at 300,000 years after the Big Bang. So again, at that moment in time, photons were all of a sudden free to travel, and they've essentially been traveling freely ever since, because the likelihood that a photon will interact with an atom becomes smaller and smaller as the universe expands. And so the photons that we detect from the cosmic microwave background have essentially been traveling uninterruptedly since that time all the way to now, when we capture them in our telescopes. And so this is a picture of what the universe looked like 300,000 years after the Big Bang. And again, it was incredibly smooth, but there were these tiny fluctuations. And the amazing thing about gravity is that as long as you have a tiny overdensity, that overdensity is going to attract other material towards it. And so things that are a little bit overdense are going to become more overdense and more overdense and more overdense until the tiny fluctuation will grow into a big fluctuation like what we see today, a galaxy or a person, right? Like, these are giant fluctuations in the overall density of the universe. These giant fluctuations come from these little tiny ones and become big through gravitational accretion, through gravity sort of attracting matter to these overdense regions. And the thing about essentially the whole history of the universe since this time to today has been a struggle between gravity, which is trying to pull things together and trying to make these overdensities even more dense, and the expansion of space, which is driving everything apart from each other. And so in these peaks, these largest fluctuations, gravity wins, and at those points you can start building stars and galaxies, and as we'll see later, clusters of galaxies. So what astronomers do in order to understand how we can form the structure that we see today from those very slight fluctuations in the early universe is essentially simulate the process in a very large computer. And what we do is we take the level of fluctuations that we see in the cosmic microwave background and their power spectrum, so how much power there is at each of those individual angular scales, and we essentially distribute a whole bunch of particles, billions of particles, in a volume of space according to that power spectrum. So there will be particles that are a little bit closer to each other and particles that are a little bit further away, but again, these fluctuations are on the level of 10 to the minus 5, so they're very tiny. And then we let the computer do the work. The computer calculates how those particles interact with each other through gravity, and it also takes into account the expansion of the universe. Now, in this simulation, this is done in a coordinate system called a co-moving coordinate system, and what that means is that the coordinate system is moving with the expansion of the universe, so that you don't actually see the expansion in this movie. That expansion has sort of been factored out. So what you're left with is the collapse of these overdense fluctuations into larger and larger structures. And you'll see, though, that the regions that are underdense, so these sort of darker regions here, also become larger and larger, because if matter rushes to the overdensities, then it sort of clears out of the underdensities. And what you're left with is this beautiful sort of filamentary structure where the filaments are intersecting each other, and at those intersections you have these very high density regions where galaxies and even clusters of galaxies, so big groups of galaxies, form. You'll see that as time evolves forward, the number on the upper left corner is decreasing. Z stands for redshift, and the redshift here is used sort of as a parameter for how for time. So as time goes forward, redshift decreases. So the amazing thing is that we can simulate this process in a computer, but we can also go out and observe the filamentary structure of the universe on large scales. So the SDSS, that stands for Sloan Digital Sky Survey, has observed and measured 1.5 million galaxies and determined a redshift for each one. And then you can plot where each galaxy is in the sky, so the sort of the angular coordinate of where the galaxy is on the sky, but then we also know, because of the redshift, how far away it is in distance. And I want to discuss this a little bit further because you might be confused as to how, based on the redshift of the galaxy, so based on how the lines of that galaxy are moved towards the red side of the spectrum, we can deduce how far away it is. And let me go through that here. So if you remember in your Hubble law lab, you guys looked at spectra of galaxies, and so this is one of those spectra for NGC 1832. That's just the name of the galaxy, and you looked at particular lines. So in this case, we were looking at hydrogen alpha, and what you did is you measured how far, so how shifted the line in the galaxy was relative to the rest wavelength, which in the case of hydrogen alpha is 6562.8 angstroms. So we'll measure that shift in wavelength, and we calculate a redshift by dividing the difference in the wavelength, so delta lambda, which is 65 angstroms. We divide that by the rest wavelength, which is 6562.8. And so the redshift, again, we can symbolize that by the letter Z, is equal to 65 over 6562.8, which is about 0.01, okay? But you also learned in your lab and in the last lecture that the redshift is just equal to the velocity of the galaxy, so the recessional velocity of the galaxy, or the apparent velocity of the galaxy, over the speed of light. So that essentially a galaxy with a redshift of 0.01 is moving away from us at 0.01 times the speed of light, or appearing to move away from us at 0.01 times the speed of light. If you remember, the speed of light is about 3 times 10 to the 5 kilometers per second, so the velocity of this galaxy, NGC 1832, is 0.01 times 3 times 10 to the 5 kilometers per second, which comes out to be 3 times 10 to the 3 kilometers per second, or 3,000 kilometers per second. Okay, so that's how we go from the redshift of a galaxy to its velocity, its recessional velocity from us. Now, how do we convert the velocity into a distance? We talked about how Hubble was able to measure both velocities through these redshifts and distances to a sample of galaxies, and how since then we've done this for many, many more galaxies and found this really tight correlation between how far away a galaxy is and how fast it's moving away from us. And we parameterize that as Hubble's law, so the velocity of a galaxy is equal to the distance of the galaxy multiplied by the Hubble constant, which has a certain value. So this tells you that once you've established what Hubble's law is, so once you know how the velocity and the distance are related to each other, then you can use the velocity measurement to estimate how far away the galaxy is. Now, you really need to have measured Hubble's law beforehand and established this relationship before you can do this, and so in order to establish Hubble's law, we had to measure distances to galaxies in an alternative way in order to actually be able to plot this and plot what velocity and distance were for a given galaxy. But once the law is established, then we can use it to estimate how far away things are based purely on how fast they appear to be moving away from us. So that's what we do here. We just measured that galaxy to be moving away from us at 3,000 kilometers per second. So that means that we extend that value out and we find that it must be at least 42.2 megaparsecs away from us. Okay? So we can just read off how far away the galaxy is based on how fast it's moving away from us from Hubble's law. So again, from the redshift we can get a distance. And now we have a map of the universe. We have a map of what the universe looks like on these very large scales at distances that are very, very far away from us. 40 megaparsecs is a very large distance, but we can go even further. So, because as you can see on the scale here, we're stepping out in redshift from the central point. Of course, at the center of the graph is us, our galaxy at the center. And then as you step out away from the galaxy, you're stepping out in radius from the central point. And 0.01 is just like, it's not even out to the first line on that scale. So, and that's 40 megaparsecs, we can go much further. And the SDSS survey, like I said, has calculated redshifts for 1.5 million galaxies. And once you plot them up in a map like this, you can see these filaments come out, these bubbles, these voids where there are no galaxies in the middle of those filaments. So the structure of the universe that we see today matches the predictions that we have for how gravity and the expansion of the universe are going to evolve and are going to affect the matter distribution with time. So galaxies form by gravitational collapse. So galaxies form by gravitational collapse, and this is again another simulation, this time a much higher resolution simulation because we concentrated all of our particles in a smaller area of space because we were only interested in the formation of one big galaxy. And so this is actually a simulation that tries to show you what the formation of a galaxy like our Milky Way was. And what you see is that the galaxy grows from a small overdensity into a larger one by accreting lots of really small things. So let's watch that again. We're zooming in. We see all these little tiny small galaxies, and those small galaxies are essentially falling into the bigger galaxy at the center through gravitational attraction. They're sort of accreting onto the central galaxy, and that central galaxy just gets bigger and bigger and bigger in size. So as you see, these galaxies are traveling in along these filaments and collapsing onto that big galaxy. So here we are at redshift 0.0, which is today, and this is approximately what our galaxy looks like today at present time. Of course, the pictures of our galaxy that we've been looking at look nothing like this one. And the reason for that is that there is no gas in the simulation, and so there is no the aspects of the galaxies, so that the gas disk and the spiral arms really aren't captured in a simulation like this. We're just looking at sort of regular matter. So again, these are simulations of how galaxies evolve. So we assume that galaxies start off as these small building blocks and become bigger and grow by basically gobbling up smaller building blocks until they become bigger and bigger, and that's what we call the process of hierarchical growth. So it's hierarchical because you start with small things and you build them up to a bigger thing. But there's another, and so that means that if galaxies are growing with time and are growing from smaller things, then as you look back in time, and also as you look out in space, you're therefore looking back in time, and so galaxies that are much further away are going to be younger than galaxies that are nearby, and so they should look different. They should look different from galaxies in the local present-day universe. They should look smaller because they start out smaller. And they should also look like they're going through a lot of activity, because as you saw in that movie, the galaxy, as it's building up, is really gobbling a lot of small things, and those small things are going to change what the galaxy is doing. And so, in fact, that's what we see when we take really, really deep pictures, like this picture of the Hubble Deep Field. This is actually the Hubble, the Extreme Deep Field. So this is an even deeper field than the Hubble Deep Field and the Hubble Ultra Deep Field. This is the Extreme Deep Field. And this is a tiny, tiny patch of sky that Hubble looked at for many, many hours, so that we were actually able to see things that are so faint. These galaxies in this image are so faint. They're really, we're looking at galaxies in the first few, less than 1 billion years after the Big Bang, essentially. So really, we're looking at galaxies when they were very young, when they were still forming, and every little smudge on this galaxy, apart from the stars, which you can identify because they have these sort of cross patterns on them because they're so bright, every other little smudge on this is a galaxy, and you can see that the little tiny galaxies are going to be really far away. And when you analyze a picture like this in any detail, you find that galaxies that are far away tend to look very different. They look smaller, physically smaller. I mean, of course, they appear smaller because the further something is, the smaller it's going to appear on the sky. But they also, once you know the distance to the galaxy, you can calculate how physically small they are. And so distant galaxies appear much smaller than local galaxies. And they also seem to be making new stars at a much higher rate than local galaxies. So they're going through this period of very accelerated star formation. So we see evolution in galaxies in the universe when we look out into the very far reaches of space and time. Even in the local universe, however, galaxies come in different shapes and sizes. In the Hubble law, I asked you to assume that to employ the standard rod assumption, which says that every galaxy sort of looks the same and is the same physical size, so you can determine how far away the galaxy is based on how small it appears. But really, that's not a very good assumption, because galaxies come in all sorts of different shapes and sizes. This is sort of a gallery of all kinds of nearby galaxies in our local universe, and you see that they look very different from each other. But one thing that you might notice by looking at this gallery of galaxies is that there are really two main types of galaxies. There are galaxies that have spiral structure, so they look like they have disks and they have these spirals in them, and they're sort of elongated, so you either see the spirals when you're looking at them face on, or you see the disky nature when you look at them edge on. And then there are these blobby ellipticals. These are just sort of spheroidal, blobby things. And if I go back to this gallery, maybe you can now start picking those out, right? So you see the spiral galaxies very clearly, and then you see sort of in the middle of all those spiral galaxies these big blobs. So galaxies sort of come in these two flavors. One is sort of a disky spiral, and the other one is this blobby elliptical. Hubble looked at a lot of galaxies and classified them according to different types on this sort of classification scheme. So on the left-hand side you have ellipticals. They come with an E, and the number increases as they become less spherical. So an E0 is sort of a spherical galaxy, and as they become more and more elliptical, that number increases. And then on the right, he sort of splits the sequence. So we actually call this the tuning fork classification, because it starts off as one single line and then it sort of splits off into two lines. On the top, they're both spirals, but on the top they're sort of regular spirals, and on the bottom they're barred spirals. So you see at the nucleus there's sort of a bar across the center. And so this is how he chose to classify galaxies. There's also other galaxies. So at the center here, in the interface between the elliptical and the spiral classifications, there are these things called S-zeros. And those are sort of things that have very strong sort of bulge-like spheroidal components, but also seem to have a disk. And so these are sort of intermediate objects between the two. In addition to these types of galaxies, there are also these galaxies that don't really look like one or the other. They're called irregular or peculiar galaxies. But let's concentrate on the two main types of galaxies. We have spirals on one side and ellipticals on the other. How are they different from each other? What are the main differences between these two galaxies that you can see? Think about it for a minute. So, first of all, in terms of color, spirals are much bluer and ellipticals are redder. In terms of shape, the spirals are disky and the ellipticals are blobby. So the ellipticals sort of look like a spheroidal collection of stars, whereas the spirals appear to be in a disk. Also, in terms of structure, spirals have spiral arms and other features, like blobs along those spiral arms, whereas ellipticals tend to be sort of featureless. They really don't tend to have many features in them. They're just sort of this smooth distribution of stars. What can we deduce from these differences? What can we deduce from the fact that, for example, the spiral galaxies are bluer than the elliptical galaxies? Which of these galaxies do you think is currently forming stars? Is it the blue galaxy or the red galaxy? Also, relatedly, which galaxy do you think has the younger stellar population? So think about it for a little bit. If you see a galaxy that's bluer than a redder galaxy, what we're looking really is at the combined light from its stars, so sort of an average of the stellar population. And we know that stars that put out bluer light than redder light tend to be hotter, right? Because as a star becomes hotter, the light that it emits shifts towards the blue part of the spectrum. That's just Wien's law that we've seen so many different times over in this course. So this tells you that the light in spiral galaxies is being emitted mostly by these big hot stars. If the stars are hot, then they have to be big, they have to be massive, and what that tells you is that they have to be short-lived, right? We're talking about O, B, and A stars. Those are the big blue stars that we see in our galaxy. So if you have a galaxy that has blue colors, that means that it has a lot of these very young stars, and that means that it must be currently forming stars today, or must have recently had a big period of star formation. Whereas if you see a galaxy that has this red color to it, so it really doesn't have many O, B, and A stars, that means that it hasn't formed stars in a while, because every time that you have a new period of star formation, you expect at least some O, B, and A stars to form, and so you would expect a bluer color in the galaxy. So this tells you, and based on how red it is, you can essentially estimate how long it's been since it's had any new stars forming, because you know how long each of these stars is expected to live, right? We know how the stellar lifetimes change based on how big and massive each star is. So that should tell you that the spiral galaxy has the younger stellar population, has been forming new stars, whereas the elliptical galaxy really has no new star formation. And so we actually call elliptical galaxies red and dead galaxies, because there's just nothing going on in them. You just have this sort of old stellar population, these old stars that are really not doing much of anything anymore. So in the next class, we're going to try to figure out why the universe makes galaxies in these two very different types. Why are there two types? Why not just one? Or why aren't there 100? Like, why do these galaxies tend to come out either as spirals or ellipticals? What's the connection between the two? Is there any? Those are the kinds of things that we're going to talk about next time round, so stay tuned.